Right now, somewhere on Earth, a stranger you'll never meet is typing a question into a glowing box. Four words. What is consciousness? Nothing dramatic, the kind of question someone types half curious, half tired, expecting an answer in a couple of seconds. They go on to press the enter key. Freeze right there. Before a single word comes back, I want you to ask something almost nobody asks. What actually just happened? Not metaphorically, physically. Where did those four words go? What touched them? How many machines? How many kilometers of cable? How many decisions got made in the time it takes you to blink? Here, ladies and gentlemen, is the truth. The ordinary question is about to take one of the most extraordinary journeys a piece of text can possibly take. It will leave the room you're sitting in, it will become a beam of light, it will pass through buildings the size of small cities, be turned into pure mathematics, get read by a system that has never seen a single word in its life, and come back transformed into an answer before you've even had the time to look away from the screen. This film follows that one question start to finish. Every stop it makes is a real physical place. By the end, you won't just know what an AI is, you'll actually understand what happens every single time when you press the enter key. Here is the first thing almost everyone gets wrong. You're not talking to a website, you're not even talking to an app. You are actually talking to an address you don't know, written in a language you've never heard of, wrapped in an envelope you can't open. The moment you press enter, your operating system hands your keystrokes to your browser. Now, your browser doesn't send your question as plain readable text, it locks it first using an encryption standard that is actually called as the HTTPS. Your browser and the distant server perform a rapid handshake and agree on a shared secret key so that everything sent from here on is scrambled into gibberish to anyone watching in between. The cafe Wi Fi, your internet provider, anyone. But your browser doesn't actually know where to send that locked envelope. It only has a name, a domain. So it asks a system called DNS, the internet's phone book, to translate the name into a numerical address. With that address in hand, your message is chopped into smaller chunks called packets and handed to your internet service provider, which passes it to the first dozen of routers, each one reading only the address on the envelope, never the contents, and forwarding it to one hop closer. From there, in most cases, your question stops being electricity entirely and it starts to become light. Pulses flashing down glass fiber optic cables, some of them running under oceans, traveling at roughly two-thirds the speed of light in vacuum. Encryption exists because the internet was never built to be a private setting by default. Anyone can listen to a shared network. DNS exists because computers navigate by number, but humans need names. And fiber exists because copper wire supply cannot carry the volume of data the modern world actually demands. Without any one of these, no encryption, no DNS, no fiber backbone, this trip either doesn't happen or happens exposed, slow, and at a scale that the internet couldn't possibly sustain. Your four words have now left the building. They're traveling as light towards a place you have never seen. So the question is, where does an AI actually live? Not the app icon on your phone, the thing itself actually doing the real thinking. It is in floating in a mist somewhere called as the cloud that people actually describe. That word is one of the most successful marketing illusions in modern technology. There is no cloud. There are buildings, real, physical, windowless buildings, often unmarked, often surrounded by fencing and cameras, frequently built near cheap electricity and a reliable water supply rather than any nearby main city. These are actually hyperscale data centers, some of them large enough to hold dozens of football fields under one roof. Cloud computing simply means renting time on somebody else's physical machine inside one of these buildings instead of owning the hardware yourself altogether. Globally, the electricity these facilities draw is now large enough to matter at a national scale. Industry energy analysts have actually tracked down data center electricity use climbing from a few hundred terawatt per hour to a year towards roughly double that by the end of this decade, with AI specific hardware responsible for most of this unsustained growth. Why built it this way, centralized, instead of everyone owning their own AI hardware? Because no one single person and almost no one single company could actually afford to build, power, and cool enough computers to hold a conversation with millions of people at once. Centralizing it into smaller number of massive facilities is the only way to make each individual conversation like yours affordable and fast. Without centralization, this kind of instant on demand AI conversations simply wouldn't exist at the price or the speed that you are actually experiencing at the moment. Your question has now found its destination. Now it needs to get inside. Past the gate, past the badge readers, past a second door that only opens once the first one is fully closed, you are inside. When you see, it isn't glamorous, it's rows, endless rows of tall metal racks, each one packed with humming machines connected by thick bundles of cable overhead and underfoot. This is the internal nervous system of the building. High speed internal networking switches moving data between machines within the facilities at speed far higher than anything possible over the public internet you just traveled throughout. Every rack needs power, and losing power even for a second is unacceptable when millions of people are mid conversation. So, these facilities run redundant electricity feeds from separate parts of the grid, backed by the battery systems and diesel generators, and can take over in less than it takes to light a bulb than flicker. And every rack generates heat, a staggering amount of it. The processes built for AI work run hot enough that older cooling mechanisms, like simply blasting cold air across the entire room, are no longer enough for the newest hardware. Increasingly, data centers now run liquid coolant in closed loops directly across the surface of the chips themselves, carrying heat far away and more efficient than air could have actually done it. Deep inside one specific row, in one specific rack, sits the machines built specifically for this kind of work: GPUs, graphics processing units. Not because your question has anything to do with graphics, but because of how GPUs are actually built, which is the whole subject of the next chapter. None of this, the redundant power, the liquid cooling, the internal networking, is optional. Software has no power supply of its own. Heat and electricity are the hard physical limits on how much artificial intelligence can exist at all. And this building's entire purpose is pushing against those limits every single day. We've found the machines. Now it's time to meet what's actually running on them. Here's the strangest fact in this entire film: the system about to answer your question has never read a single word, not one. It has never seen a letter. So you might ask yourself, how does this understand you at all? What actually sits in the GPU's memory is not a program with instructions, right? And it's not a database of stored answers. It's a colossal file of numbers, and upwards of hundreds of billions of them, called parameters, shaped months or years earlier by a training process that is already finished by the time your message actually arrives. Before any of those numbers can do anything, your sentence to stop has to stop being a sentence, right? It gets chopped up into small chunks called tokens, sometimes whole words and sometimes only word fragments, like breaking your question into a fixed set of logo bricks so a machine that only understands numbers has something to actually hold on to and process that request. Each token is then converted into an embedding, a long list of numbers representing that fragment's meaning as a location in that particular space. Imagine every word and concept the model knows plotted as a point in a space with hundreds of dimensions, related ideas cluster and all working simultaneously with each other. King sits near queen, hot sits near warm, and far from glacier understanding. And at this level, it isn't reading, it's actually geometry. Then comes the part that changed everything. Attention, this, right? Picture every token in your sentence as a person in a room, and each one is simultaneously judging how relevant every other token is to all of it at once, not left to right. That's how the world that's how the word bank knows whether you mean a river bank or a savings account. By weighting its relationship to every other word in the sentence, it's parallel instantly. This mechanism sits inside an architecture called a transformer, and it's the reason modern AI can hold context across a long conversation in a way older system could possibly never hold. At first principles pause, because this is the part worth truly understanding, is why does this require thousands of specialized chips instead of the ordinary processor in your laptop? Because generating even one token means multiplying enormous grids of numbers together repeatedly billions of times, and this cycle repeating for thousands of times in every single day. Why grids of numbers? Because embeddings and attention represent meaning as lists and tables of the numbers, and a grid of numbers is mathematically a matrix. Why does a GPU handle that so much better than a regular processor, you may ask? Because a regular processor, a CPU, is built to execute one complex instruction after the other, extremely fast, one at a time. A GPU is built the opposite way. Thousands of small, simple calculators all firing at the exact same instant, originally designed to color every pixel of a video game screen simultaneously and run the commands together. It turns out that color every pixel at once and multiply every number in a giant grid at once are the same kind of problem. That's the physical reason your question needed a building full of GPUs and not just one mere laptop. The model's parameters are the product of training. The model was shown enormous amount of text and through millions of small corrections gradually adjusted those hundreds of billions of numbers until they became reliably good at one specific task that the user could actually give, predicting a plausible next token. Its context window is simply how much of your current conversation it can hold in a view at once that while working on a memory that resets between separate conversations. Without tokens, embeddings, and matrices, language could never become math in the first place. Without attention, a model could read your words but never weigh how much they can relate to each other. And without GPUs built for parallel arithmetic, none of this could run at a speed anyone would wait for. The model now finally has your question, now as words, but not as words merely, but as pure structural mathematics, the way it has to be decoded for it to actually solve that particular task. Let's see what happens next. If the model finished training months or years ago, how can it know anything about the last week? And when it answers, it is looking at things up the way you would. Training is the years long, extraordinarily expensive process of shaping those billions of parameters right. And it's already happened, it's finished, and it is not what's occurring right now. Interference is what's actually happening. Using those already frozen parameters live to generate a response to your specific question one token at a time. Think of training as years of schooling, reading, studying, absorbing patterns, and interface as the exam itself, using everything that you've actually learned on spot without necessarily opening a new book. That means by default, a model's built-in knowledge has a cutoff, a point after which it was simply not trained on anything newer because the data simply didn't exist when the training actually happened. But by default is doing a lot of work in that sentence, because different AI systems bridge that gap in different ways, and this is the most important to say precisely because it's one of the most misunderstood parts of how these systems actually work. Some systems can perform what's called retrieval augmentation generation, right? Which is fetching relevant text, a document, a web page, a file, and inserting it directly into the model's context window before it answers, effectively handling its reference material during the exam or the instruction given by the user itself. Some systems can also go one way further and use external tools mid conversations, running a calculator, searching the web, and checking a live data source, checking data online, and folding the results back into one particular answer that is actually valuable to the user. Not every AI system does this, not every conversation triggers it, even in the system that it can possibly do. Some models only search when a question seems genuinely, some of the question requires some genuine current context or current information. Others don't have that capability at all. The exact behavior depends entirely on which system you're using and how it has actually been configured. There is no single universal answer to does this AI search the internet. It depends on the product that is actually in front of you. Why does any of this exist at all? Because a model frozen at its training cutoff would grow more outdated every single day it actually remained in use. Retrieval and tool use exist specifically to close that gap between what a model actually learned once and what's true right now. Whichever path applies, pure trained in knowledge, retrieved reference material, or a tool's live result, the model now has everything it's going to be using, right? It's ready to actually build the reply one predicted token after another. The instant the very first word of the answer is actually decided, how does it actually go from number inside a chip to a letter on your screen less than few seconds later? The same GPUs that just processed your question now run in the opposite direction, not analyzing tokens but actually predicting them one at a time. Each new token is chosen based on your original question, and every token the model has generated so far in its own answers, including the ones that it just wrote a moment ago, it cannot see its whole answer in advance. It's discovering it the same way you are actually discovering a sentence by speaking it aloud, one word informing the next one. Each finished token is converted back into readable text and immediately streamed, sent back over to the same kind of encryption connection, broken again into packets, retracing the same route in reverse, back to the data center's network, out into fiber optic lights, back to the routers, back to DNS resolved paths, back to your internet service provider, arriving in a small burst of information at your browser right in front of you. Your browser then does the final, almost invisible piece of work, which is taking that incoming text and rendering it at pixels on your screen using your own device's processor. That's the typing effect you see appearing in real time. It isn't a performance built to look impressive. It's literally the model finishing its thought while you watch, each word arriving the moment it's generated, not a moment before. Streaming exists because making you stare at a blank screen for several silent seconds while an entire answer is generated in the background would feel broken. Even if the total time was identical, seeing it arrive word by word is what makes an enormous, continued, genuine spanning process feel absolutely instant. The round trip is actually complete. Four words went out, an answer came back, and somewhere in the middle of that ordinary feeling of exchange, an entire planet's worth of infrastructure just did its job. So, what did that four word question actually cost the world? Not in a price you saw, in electricity, in hardware, in physical infrastructure running non-stop for millions of people all at once, of which one exchange was a tiny, practically invisible fraction that you actually exchanged. Independent researchers who study this, because notably most AI companies don't publish the exact numbers themselves, estimate that a single typical AI response consumes somewhere in the ballpark of a third of a watt hour to under a watt hour of electricity, roughly comparable to or somewhat more than a single web page search. It sounds like almost nothing. It is almost nothing. Multiplied by billions of questions every single day worldwide, that is where it gets a little dangerous. Because when you zoom out further and the picture gets very vast, energy analysts at the international energy agencies have tracked global data center electricity and demanded heading from a few hundred terawatt hours a year towards roughly a double of that by the end of the decade, like I already mentioned, with AI hardware driving most of that growth and development. Some industry projections suggest that specialized chips powering AI alone could eventually consume electricity on the scale of an entire mid sized country. This is actually incredible. And these are estimates and not fixed facts, right? So I'm just citing these estimates from the internet as I when I discovered them. The real numbers move constantly as hardware gets more efficient and obviously the demand keeps increasing and there is new innovation. But the trend line is not in dispute. Picture it like a highway at a rush hour, right? No single car or no single vehicle actually causes the traffic, but the highway itself, the fiber optic backbone, the data centers, the power plants, the cooling systems, the fleet of the GPUs, and has to be built enormous enough to carry every single car, every direction, every hour, in every time zone without ever fully stopping efficiently. All of that, the buildings, the cables, the power station, the cooling loops, the billions of parameters, the thousands of chips built to multiply grids of numbers in perfect synchrony, exist to do one thing: compress something that would have taken a trained expert years to learn into, and reply reaches you in under 2 seconds. So go back to where we started. Someone typed what is consciousness and pressed enter. The system that answered them has no memory of yesterday, no body, no experience of being alive, and yet to produce even a fluent, thoughtful sounding guess at one of the deepest questions humans have ever asked, it quietly recruited a chain of infrastructure spanning oceans, buildings the size of small cities, and enough electricity to matter at national scale. The next time you press enter, you'll know exactly what got you started. A journey through light, through concrete, and through steel, through liquid coolant, to billions of learned probabilities out and back. Before you've seen or looked away, you have the answer sitting right in front of you.